All right, welcome back to another episode of Science with Surback. Today what we're going to be discussing is section 12.1, which deals with the topic of stoichiometry. Now before we get going into the details of this video, here are a couple of objectives I want you to be able to accomplish by the end of this lesson. So objective number 1, identify the quantitative relationships in a balanced chemical equation. And objective number 2, determine the mole ratio from a balanced chemical equation. All right, so we get underway here with a term called stoichiometry. And so stoichiometry is defined as the study of quantitative relationships between the amounts of reactants and the amounts of products formed by a chemical reaction. Now, stoichiometry is based upon the law of conservation. And this law of conservation states that matter is neither created or destroyed. So, because matter is neither created or destroyed, there's a couple things we need to talk about in chemical reaction, or what happens in a chemical reaction. So the first thing that happens is chemical bonds in reactants break. Once those chemical bonds in those reactants break, new chemical bonds are going to form to produce products. Now, during that process of steps 1 or 2, or in the process of a chemical reaction, it's important to remember that the amount of matter present at the end of the reaction is the same amount of matter that was present at the beginning. And then the other important point that I want to make here that's tied very, very closely to stoichiometry is that the mass of the reactants equals the mass of the products in a chemical reaction. Okay, so now that we have some base knowledge on stoichiometry, what we need to do here is shift gears and start talking about how we can relate stoichiometry to balanced chemical equations. So we'll shift gears here to our next page. And we start out here with an example reaction where we have solid iron reacting with oxygen gas to produce our iron 3 oxide or rust. Now, I want you to notice here that the equation is not balanced. You need to get in the habit, whenever you see an equation, a chemical equation, you need to make it sure it's balanced, and if it's not, just go ahead and balance it. So we start out here with this. We start out with our iron. We have 1 iron on the left, 2 on the right. Now I'm going to use pencil because we might have to go back and recorrect that. So that means we need a 2 out in front. We move to oxygens. We have 2 oxygens. Over here we have 3. Well, one is an even number and one is an odd number. And whenever you get this 3-2 combination, the best way to deal with this is place a coefficient of 3. So I have 3 times 2, a total of 6. And now my goal here on the right is to get to 6. So what times 3 equals 6? Well, 2. So now our oxygens are balanced, but this has made our irons a total of 4. So no longer does this need to be 2. This iron over here on the left needs to be 4. So our coefficients are 4, 3, and 2. Now, we need to have some type of interpretation of this balanced chemical equation. So our first interpretation is going to be in terms of representative particles. So if we go through representative particles, we're going to have 4 atoms of iron, or Fe, and that iron is going to react with 3 molecules of oxygen. And when 4 atoms of Fe and 3 molecules of oxygen react, what is going to be produced is 2 formula units of that iron 3 oxide. Now, we can also interpret this chemical equation in terms of moles. So if we interpret it in terms of moles, we are going to have 4 moles of iron react with 3 moles of oxygen to produce 2 moles of iron 3 oxide. So the point of this is that our number of representative particles and moles can be interchanged. So when we have this coefficient, it's not only representing those number of particles or atoms in the case of iron, it's also representing the number of moles. And that is very important as we go forward throughout the rest of this year. Now, what we need to do is we need to apply the law of conservation to this equation. So we start out here with our reactants. And the first reactant that is listed is Fe. Well, our balanced chemical equation says we have 4 moles or 4 atoms of Fe. We also have 3 molecules or 3 moles of oxygen. Now, because oxygen has the formula O2, we actually have 3 times 2 total moles of just oxygen. So that is a total of 6 moles or 6 atoms of oxygen. Now we need to talk about our products. On the product side, we're going to do a very similar thing. We have 2 times 2, so that means either 2 moles of Fe, 2 times 2, 4 moles of Fe, or 4 atoms. And then we do a very similar thing here. We have 2 times 3, which is a total of 6 moles or 6 atoms of oxygen. So my point is this. The number of moles of each individual element is equal on the left and right hand side. And that's what we've been doing by balancing the chemical equation. All we're doing now is we're saying, hey, we can apply this concept of the mole and relate it all together in a balanced chemical equation. So now what I want to do is I want to prove that through math, we have equal amounts of elements on the left and right hand side, and we're going to do that using the math. So we'll transition here to be able to. Okay, so the steps to determine the mass of the reactants and products are as follows. Number 1, balance the chemical equation. The second step is determine the number of moles contained in each of the reactants and products. Now, the number of moles is equal to the coefficient. The third step is to convert the moles of the substance to grams. To do this, it involves the molar mass. Now, once you've converted all the moles to grams of every substance in the chemical equation, you're going to need to add the masses of the reactants together. And just as you did for the reactants, you're going to need to add the masses of the products together. The sixth step is to check to make sure that the mass of the reactants equals the mass of the products. Okay, so let's go ahead, let's try these 6 steps on an example problem. So, luckily for us, what we have here is the same equation that we've been working with. So if you remember this, to balance it, I'm going to start on the right actually. We had a 2, then we had a 3 in front of O2, and then we had a 4 in front of Fe. So we balanced the equation, that is step 1. And now to help you out, we need the molar mass of each of these substances here. So I already went ahead and calculated the molar mass. So the molar mass of Fe is 55.85 grams per mole. O2 has a molar mass, because it's a molecule, a molar mass of 32.00 grams per mole. And then iron 3 oxide has a molar mass of 159.70 grams per mole. So the next step here is to write down how many moles of each substance we have. Well, simply the number of moles is equal to the coefficient. So for our first reactant here, we have a coefficient of 4, which means we have 4 moles of Fe. Going to give a little space here. Going to go to our next substance, which is O2. A 3 coefficient means we have 3 moles of O2. And then the last thing we have is our only product, which is 2 moles of Fe2O3. So again, the coefficient is just the number of moles in this particular case. Okay, now the next step is to convert each of these substances to our grams. And the way we do that, remember, we cancel out moles on bottom, so moles of Fe. The molar mass would go on top, so you'd have 55.85 grams of Fe. And I'm going to punch that into my calculator. So we have 4 times 55.85, and that gets us a value of 223.40. So 223.40 grams. And I go through and do the same thing for oxygen. So I get rid of or cancel out moles. So 1 mole is going to go on bottom. And then the molar mass, remember, oxygen's a molecule here, so it's 32.00 grams of O2 to every 1 mole. And that's the value I use from up top here. So again, all I'm going to do is take 3 times 32.00, press enter, I get a value of 96.00. So 96.00 grams. And I move down to our Fe2O3. Again, I want to cancel out moles, so I put 1 mole of Fe2O3, and I put the molar mass, which is 159.70 grams of Fe2O3. And I plug this into my calculator. So I take 2 times 159.70, and I press enter, and I get a value of 319.40 grams. Now we need to make sure, we have all the masses, but we need to make sure that the mass of the products, the mass of the reactants equals the mass of the products. Okay, so our 2 substances involved in our reactants is iron, Fe, and O2. So I'm going to put a note here. I'm going to put the mass of the reactants. How we do this, we take the number of grams contributed by Fe, which is 223.40 grams, plus the value or the amount of grams contributed by oxygen, which is 96.00 grams. So we put that into our calculator. So 223.40 plus 96.00. We press enter. We get a value of 319.40 grams. So 319.40 grams. That is the mass of the reactants. The mass of the products. It's really easy. It's really easy because we only have one product. That one product is iron 3 oxide, or Fe2O3. So the value here, we actually don't need to do any adding. The value of the mass of the products is 319.40 grams. Now comes that check. Is the total mass of the reactants equal to the total mass of the products? The answer is yes. So let me make this known. Let me state this. The mass of the products is equal to the mass of the reactants, which is 319.40 grams. All right, so there's that written statement here. We just proved that the mass of the reactants equals the mass of the products, and in this example, both were equal to 319.40 grams. All right, so that's how we prove that we can abide by the law of mass. Now what we're going to transition to is what we call mole ratios. Okay, so moving on to the mole ratio, all right? So the mole ratio is defined as a ratio between the number of moles of any two substances in a balanced chemical equation. So it's important to remember that in chemical reactions, the coefficients indicate the relationship among moles of reactants and products. So to be able to determine the mole ratio of two species or substances, we need to look at the coefficients in front of each species or each substance of our chemical reaction. All right, so let's try this out in an example of where we're going to find these mole ratios. So in this example here, we have potassium chlorate decomposing into potassium chloride and oxygen. First thing that you should always do is balance the chemical equation. That should be the first thing from here on out to be able to do. So what we have is this. We have 1K on our left, 1K on our right. They're balanced. 1 Cl on our left, 1 Cl on the right. They're balanced. And now we get to oxygen, all right? We get 3 on our left, 2 on our right. Again, the 3-2 combo. Always try to meet at 6. So we're going to try to put a 2 coefficient. So we have 2 times 3, a total of 6 oxygens. To get 6 oxygens over here, we're going to put a 3 in front. Now we have 2 potassiums, 2 Ks. So that means over here we need a 2 out in front. And looky there, that balances our Cl's out. So now we are balanced. So what we need to do is the problem told us, hey, determine all the mole ratios for the reaction. So what we're going to do here is we're going to have a mole ratio between each substance. So the first mole ratio I'm going to do is going to be between potassium chlorate and KCl. So I'm going to put KClO3. I'm going to put a colon to KCl. And below here, I'm going to put the mole ratio. So below here, we look to the balanced chemical equation. So for KClO3 and KCl, we have 2 moles of KClO3 to 2 moles of KCl. Now, we're going to look at the mole ratio between KClO3 and O2. Okay, so out here I'm going to put KClO3 colon O2. And to figure out the mole ratio, what we're going to do once again is we're going to look to the coefficients. The coefficient number becomes our number of moles. So in this case, we're going to have 2 moles of KClO3 to 3 moles of O2. So we have 3 moles of O2. Now, there's one more mole ratio in this particular problem, and that's between KCl and O2. So here we go again. We're going to write KCl colon O2. And again, to get our mole ratio, we're going to look at our balanced chemical equation. So the coefficient becomes the number of moles. So we have 2 moles of KCl to 3 moles of O2. So we have 3 moles of O2. And that's our mole ratios. Now, I know I've done this problem before, so I know my stopping point when I'm done. But if I give you an equation and I say, hey, go find the total of number mole ratios, what you are going to need to do is you're going to need to be able to determine the stopping point. Now, I want to talk about one thing, and that one thing is this. The total of mole ratios would actually be double. And the reason it is double in this case here is every one of these mole ratios could flip-flop. So let's say here now I have KCl to KClO3 we flip-flop our numbers. And it may not seem like a big deal here because it wouldn't be a difference of the value here. But if I flip-flop this, if I said O2 to KClO3, we would flip-flop our values. And then same thing here, that would have an effect here. So our mole ratios can also be flip-flopped. So our other mole ratios would be this. I'm just going to flip-flop each of these things, and I'm going to have KCl to KClO3. Now, I told you before, number of moles, so you get 2 moles of KCl to 2 moles of KClO3. Now, again, we're going to flip-flop here. So our mole ratio, or our values that we're finding, is O2 to KClO3. So our value for our mole ratio here would be 3 moles O2. So 3 moles O2 to 2 moles of KClO3. And then our final mole ratio here that we need to find is going to be O2 to KCl. So our mole ratio here, again, moles in front of O2 is 3, so 3 moles of O2 to how many moles of KCl? 2 moles of KCl. And this right here becomes all of our mole ratios. So again, I forgot to flip-flop them. And these right here, so these 6 values would be all of our mole ratios. Again, like I said, I've done this problem, so I know the stopping point. You should have a total of 6 mole ratios for this particular equation. But how you know the stopping point is very important. So we'll shift gears here, and we'll go to predicting the total number of mole ratios. Okay, so to determine the total number of mole ratios present in a reaction, multiply the number of species or substances in the chemical reaction by 1 less number. All right, so let's try this in an example where we have the combustion of methane. So in the combustion of methane, methane CH4 reacts with oxygen O2 gas and produces carbon dioxide and water. Now, the first thing we need to identify is those species, or these substances. So each thing, each reactant, and each product is a species. So I'm just going to make this clear here, that each thing here, each item that we deal with, is going to be a species. Okay, so these things here are all species. So all we need to do to find the total number of species is count them. So we have 1, 2, 3, 4. Now we don't include the coefficients, we just include the substance itself. So in this particular equation, we have 4 species, and we multiply that by 1 less number. So that means 1 less number than 4 is 3. 4 times 3 is 12. And so that gives us our total number of mole ratios. So we should have 12 total mole ratios. Again, remember, the thing I forgot to do is flip-flop your ratios. So it may seem like you have them all, but you flip-flop, you reverse what you have, and that allows you to get your total number of mole ratios. All right, so we introduced a lot. This is really important as we move forward with stoichiometry. Hope you have enjoyed this episode, and if you haven't already, make sure you subscribe.